So this chapter, this series of videos in chapter 18, focuses on spectroscopy. You've all done spectroscopy before, you've thought about it, but maybe not in the level of detail that we'll talk about here, both from the perspective of what are the variety of different types of light matter interactions, which is the definition of spectroscopy, what types of interactions dominate different regions of the very broad electromagnetic spectrum. How is light generated? How is light of different frequencies generated practically? And then ultimately we'll get to thinking about the different geometries of a spectrometer. How is a spectrometer built? How does it work? And so certainly some of the basics associated with that. We're not going to dive in too deep because that is reserved for the instrumental course. If you go on to take 342, you'll build one. If you take my class, you'll build one from scratch over the course of a week. But here I just want to give you a general sense, because you use these things all the time. How do they work? What chemical phenomena are occurring, physical phenomena are occurring in the molecules when they absorb light, how you should think about doing spectroscopic measurements, and ultimately what leads to error. If you don't fully understand the technique, then almost certainly you're going to misapply it. And so the goal is to give you a basic understanding of a wide variety of these things. In order to do that, I think it's easier to start and think about how the light around us is created, and then how that light is used in the electromagnetic spectrum to interact with different light. And so that topic is called Blackbody Radiation, and this comes from Max Planck. He was the one who eventually developed exactly what you're looking at here. This figure comes out of your textbook. And the phenomenon is a little, it's interesting. You know what it is because you've seen it, but you probably never knew what it was actually called. So blackbody radiation, generally speaking, it just means that if you have an object, a perfectly black and dark object, meaning it's not shiny, it's not reflective, it's perfectly opaque and black and dark and not colored. If you heat that object up, then it's going to produce light. And specifically blackbody radiation, and what Planck showed is that both the power density, so the watts per square centimeter, or the power per area, both that and the actual frequency of that light that gets generated is a function of its temperature. And that wattage, or that power density, scales with temperature to the fourth. It's not important you know that, but just know that the power is highly dependent on the temperature. And what you see are just ideal black bodies, and I say ideal because there's no such thing as a perfect black body. These are hypothetical objects, but what we'll know is that many things in reality and life around us mimic black bodies, even though they're not ideal. They may deviate slightly, but their general properties are still true. And so what Planck is showing in this figure is that the power density, which is what this log m wavelength is here, this is a log scale, so this is growing fast, exponentially, right? And then we have the semi-log plot down at the bottom here, which is wavelength in microns, which is not super useful because nobody uses microns. But anyway, what you see are the two things that I just told you. As the temperature, which is in units Kelvin, for each of these lines, as the temperature of that object, physical object, goes up, both the peak, or the lambda max here, where you start to see the peak power density, that starts to shift to lower wavelengths. And both that and the power density itself start to shift as we crank up the temperature of that object. And this is really important because, you know, the places where you would have seen this are like if you have a flaming red hot piece of metal. You may not have seen that in real life, but if you were a blacksmith, you would have. So simply just heating up this object, this metal object. On the left you have actually a solid piece of metal, on the right you actually have it molten. So the one on the right's a little hotter, and you can see the colors, the actual spectrum is changing, and so is the intensity. If you have just a hot piece of metal, right? If you've ever taken a piece of metal and put it in the fire, it very slowly starts to glow, but that glow is not that intense. but as the temperature, if you leave it in the fire longer, the glow gets brighter and brighter and brighter, and that's because of blackbody radiation. As the temperature goes up, the power density, the amount of photons being liberated from that object, being sent to you because they're being converted from heat energy into light energy, it goes up with T to the 4th power. So you can see that the molten metal is even brighter. But what you also see is that the color of molten or of hot metal actually can give you a sense for what the temperature of that object is. So there's tons of tables out there that you can see that blacksmiths use where they look at the object and its color, and that color actually gives you a sense for its temperature. This is sort of the origin of like something that's called white hot, because what you're doing is going from sort of this dark color, which isn't really dark, it's just imperceptible to our eye. Those are infrared photons. That's what's sort of shown on Planck's plot here. So as you heat this object up, you can see the band is moving, that lambda max is moving towards the visible light. And so if you've got an object and it's at 1000 K, it doesn't mean it's hot just because it's not glowing. It could be super hot, right? We've all touched a hot pan, but it's not glowing hot. That's simply because its centroid of emissivity, where it's emitting most of its light, is in the infrared range, which, what do we know infrared light to be? It's heat, right? So it's emitting photons in long wavelength, which are the same as heat, or we perceive them as heat when we absorb them in our bodies. As you keep cranking up the temperature of this thing, then you start to go from red, which are the sort of reddish orangish hues, and as you keep pushing the temperature more and more, it starts to glow more white, because you can see, like for this 5000 K example, the centroid's right in the middle of the color spectrum, visible light spectrum, where Roy-G Biv is. And so you're emitting all of those lights simultaneously. If you're emitting all different wavelengths of light more or less equally, you have white light, which is what white hot means. So the chart that I have over here is actually a little bit more sophisticated, where it gives you the temperature on the left axis, the y-axis, the color that you would perceive, and then the percent carbon that you have. And then inside written here, which is pretty awesome from a material science perspective, which I am, it also gives you the process that you're undergoing, which is a phase change or a phase transition inside of that metal. Actually overlaid on this, all these lines, this is the phase diagram for carbon, steel, with different percentages of carbon, and then overlaid on the background is the color. It's pretty mind-blowing. It's really cool to be able to see it like that. And so this is blackbody radiation. Why do I bring it up? Because we're going to talk a lot about light, and I want to give you some perspective about how light is generated. Like the sun, of course, is this giant blackbody radiator where it's super hot because of fusion in the core, and it's radiating the spectrum that we see as all of light around us, right? The whole idea of visible light comes from our definition of how much of the light from the sun is being emitted in those ranges. So let me show you a quick demo. This demo comes from PhET, or PhET, comes from CU Boulder, from a physicist there, and they're awesome. I really love these animations because they actually take the mathematical expressions that define a phenomenon, and they animate it in a way that it's interactive, and it really gives you a sense for what's going on in the system. And so what I have here is the spectral power density in megawatt per meter squared per micron, and that is the value that I was showing you in the Planck equation, or the Planck plot in the previous frames, and then as a function of wavelength here. This isn't the semi-log plot, but the regular plot in microns. So what we see is that we have the ability to change the blackbody temperature, and the default is the sun, just because that's what we're all seeing. And we can overlay onto that where the visible light range would be specific to the colors of those light. We can change and overlay the actual intensity, which would be the integrated plot here, and that gives us a numerical value. We can apply labels if we want. I might leave those just for fun, and then we can actually ascribe values, which would be our peak values here, both on the x and the y-axis. So what you can do is change the temperature, so I can just lower the temperature, and what we can see is in real time, we have this value labeled. Its peak value is at 0.5 microns. But as I decrease the temperature of this body, not even by that much, you can start to see the wavelength, the peak wavelength of this grow as the whole thing shifts further and further to the right. And now it becomes really pronounced as we move down towards a light bulb. And by light bulb here, they mean incandescent bulb. And I'll talk about why that is, why it's not an LED or a compact fluorescent here in a second. So I'm going to zoom back in here. We're at quite a bit lower spectral power density, of course, because of light bulb versus the sun. But now you can see that only a little bit of the power that's being emitted from a light bulb is actually in the visible range. That most of an incandescent bulb is emitting out in the infrared. Why does that make sense? Well, you all may be too young to have used tungsten filament incandescent bulbs, but when I grew up, all bulbs were that way. And we knew that you don't touch them because they're too hot. The reason that they're hot is because at that power density, most of the photons that are being emitted from that black body are in the infrared range, which we as humans, our skin absorbs those things. I'll talk about exactly what happens to your skin when you absorb infrared light, but our perception of that is heat. And so we can keep moving down further and further on the system. It keeps shifting further and further into the red or into the infrared here. And you can see all the way at the bottom we have the Earth, which you can see that the Earth itself is an emitter, but not by very much. And actually it shows that the scale is down at the bottom, but that's not true. All objects around us, these pens, this can, all of these things are at a temperature. So they are emitting some spectrum and have some spectral power density associated with them. But as you can imagine, this thing, because I'm holding it, is not hot. This is room temperature. This is a blackbody emitter as well, but its frequency has shifted so far into the long wavelengths that it's emitting things that are imperceptible to us. And so if we turn off the lights, we're not going to see this glow. It's not going to do anything that would change. So hopefully this gives you sort of an intuitive sense of how light is generated. And specifically, when we're talking about like sunlight here, and we look at this, this blackbody spectrum, what's important to know, and I'm going to talk about this later, I'll refer to this type of light, this type of light source is what we call broadband, because it has a continuous emission of all the different spectra, photons of light in the visible range, and not just some discrete bands, which we'll learn about. This broadband source is not the same as something like an LED light source, which are much more energy efficient, but as we'll see, do not contain all of the frequencies of visible light. In fact, they only contain 3, and they lie to our eyes and convince us that it looks like white light, when in fact it's just carefully engineered blue, green, and red bands, singular atomic bands that we're seeing. They'll talk about that, but this is considered broadband light. Any blackbody emitter is considered broadband light for this reason, because it's emitting over a continuum of wavelengths that are associated with the spectral power density here, or the distribution of